As always, this is Grant Davidson here, one of the applications engineers here at TMS CADCentre. And today, in our How Well Do You Know Your Mates webinar, we'll be focusing on the SOLIDWORKS range of mechanical mates. Now, we'll go ahead and jump in. I did then, of course, have to determine what was going to be the best way of showing you guys this collection of mechanical mates, and decided that an elaborate flag-waving machine encompassing all of the mates was the way to go naturally. Let me show you here, just a little bit of something I knocked up. As you can see, flag's going to move about. It's quite an elaborate machine. As you can see, we're going to go through a series of gears. We've got a cam on there. We're going to introduce a belt. We've got a rack and pin type arrangement. We've got universal joints and so on. I'll run through it a little bit with you here, and I'll show you what we'll be covering today. But it's all kind of encompassed within this machine. So this is what we'll be using for the webinar today. Now, it's been dubbed the TMS machine. I do welcome more creative names via email, please. That would be great. But what do we actually have in this TMS machine? Well, we start with some miter gears. Now, these miter gears, as you can see at the moment, they're just sitting in there. But essentially, we want these to turn with a gear-like motion. That will then transfer a torque through a shaft into a linear set of gears, which drives a rack and pinion arrangement at the bottom. From there, we drive a secondary linear gear, which again is onto a fixed shaft, which resultantly is going to turn a belt on a pulley and finish by rotating a cam. And, of course, on the cam follower, we have our flag. Now, in addition to that, we're also going to add in a universal joint, and that universal joint should move in unison with the other yoke you see there, and that's all going to be secured in with this bolt. So, quite a packed webinar for you guys. And what's it actually going to be about? Well, at the moment, I've built the assembly, as you can see, but there are no mates to describe the mechanical movement of it. So that's going to be the focus of the webinar. How do we describe that? Well, first, let's get our miter gear moving as it should. So the way that we do this, as the minute, you can see I've went ahead and put the gears in. But just because I've got gears in there doesn't mean I've necessarily told the system what they are or how they should interact with each other. We all know the teeth should kind of slot between each other nicely, but the system doesn't know that at the minute. How do we actually tell the system this? Well, what we can do is if we go up and just click on our mates dialog here, what we're looking to add isn't necessarily a standard mate, so we can minimize that down. What we're looking for is mechanical mates. Now, if we expand this dialog out, in there, what you'll find is gear, which allows us to add in a gear mate. Now, the selections are very simple. Simply just go ahead and select two diameter sketches or edges, in my case here, as you can see. Select two which describe the gears. SOLIDWORKS will automatically pick up on the ratio of those gears, 85mm each in my case, or we could simplify that to a ratio of 1:1 because they are the same size. If you did want, say, one gear turning at twice the speed of the other, you could maybe put a ratio of 2:1 in there. Beyond that, you can also choose to reverse the direction of the gear, which would have them turn in opposite directions. We'll leave that unchecked for the moment and just click OK. Now let's exit out that mate dialog and see what that's done for us. Now if I grab, let's say, gear A, notice it does turn gear B as we would expect, but the whole time we're getting interference in there. Now it is turning as we want, but that interference obviously is not acceptable. How do we handle that? Well, once again, just because we've put a gear mate in doesn't mean we've told SOLIDWORKS avoid any interference. How do we actually avoid the interference? Because obviously it's not what we want. Well, if we go back in and just choose to temporarily remove that gear mate, good practice is to go ahead and set your gears up beforehand. So as you can see I'm doing here, I'm just going to align my teeth together. That way we're not going to have any interference. I want this tooth to sit between the other two on gear B. So I position it just as I want, and then I can go back and bring in that gear mate. Now we are just doing that by eye at the moment. I'll show you how we can do it more accurately on our linear gear. But if I go ahead and bring that back in, then try twisting that gear, as we would expect, we're then not going to get any interference and we're going to get a realistic gear movement. Now notice the miter gear is indeed turning, and that is resultantly turning the shaft. But my linear gear is still staying still. This doesn't suggest the absence of a mate, but instead just that the concentric mate connecting the gear to the shaft doesn't have its rotation locked. If we were to access this pre-existing mate, we can choose to turn the option to lock the rotation on. So if I go ahead and locate this component, there it is there, my metric spur gear. If I go in there and just find the mate that mates the gear onto the shaft, as in that concentric mate, and choose to edit that, in there what you're going to find is an option to lock rotation. Now if I choose to lock rotation, just as it says in the tin, it will go ahead and lock the rotation of the gear to the shaft. And what that resultantly means is if I turn that shaft, the gear is now locked to it. Relatively simple. Let's turn our attention to the rack and pinion arrangement now. Now the first thing to do, once again, good practice, as I've told you guys, is to align our pinion with the rack so that we avoid interference, just like in the spur gears there. So we'll align that. Then what we want to do is, say we want to align it slightly more accurately. Say we don't necessarily want to do it by eye, but we actually want our spur gear's tooth to touch on one of the little spikes in our rack. Well, what we could do is go in and use our move component command and make use of that there, the collision detection. Move your cog or your gear until the tooth hits the rack, and you can then stop it there, and that will allow you to actually have contact before the rack moves. Just an extra idea for you guys, but at the moment we'll stick with it, just doing it by eye. That's sufficient for what we're trying to do. So what we're then ready to do is go ahead, access our mate dialog. Under mechanical makes, you'll find rack and pinion. In here, again, simple selections. For the rack selection, select an edge which describes the full length of your rack. Select a linear edge. Now in my case, I'll select that bottom edge. And for the pinion or the gear, well, what we want to do is select a sketch which describes the overall diameter of our gear. So if I go in and turn on sketches here, would help if I actually turned it on there. I think I missed the button. If I go ahead and turn my sketches on, what you'll see is I've added a construction circle in there. Now that's a perfect selection for our pinion or gear because it describes the overall diameter including the teeth. So if I select that, click OK, what we'll then find, if I go ahead and move this gear, sure enough it is moving as we would expect a rack and pinion arrangement to, but it's going in the wrong direction. Now that takes us back to that little checkbox of reverse. So if I go back to that pre-existing mate, the rack and pinion one we just added, edit that, go in there, and I want to reverse the orientation of that mate. I just check in that box and it'll do so for me. Now your rack may kind of speed away there, but that's okay, it's just a result of reversing the mate. But if I go ahead and just turn this gear, what we will find is our rack will come back into place, and as you can see, acts as we expect a rack and pinion to. Now I don't think my rack fits quite nicely, but don't tell anyone. For the purposes of demonstration, it's okay, but I don't think it's a perfect fit, to be honest with you guys. But that is reacting just like a rack and pinion should. So looking well there, let's turn our attention now onto the linear gear then. Before we do so, let's try turning right back at the beginning, make sure everything turns in unison, and yeah, it does. All looking fine. So our linear gear, let's turn our attention to that. We'll turn off the sketches just to clean up the display. And in this one, again, good practice, we're going to go ahead and align the gears. So this same thing, time and time again, we'll just align these teeth so we're not getting interference. Again, we'll just do it by eye. We don't need it too accurate. For all intensive purposes here, that'll be fine. And again, we're just going to go back to our mate dialog, and we want to select two reference diameter sketches, if you remember, in the gear mate dialog. Or in my case here, just to show you guys something different, I've put a couple of split lines onto my gears. Makes no odds. Use a split line, use a sketch, use whatever you're comfortable with or whatever you happen to have in there with your geometry. And again, I'll use a ratio of essentially 1:1. 63 mil, just happens to be the size of my split line. Click OK, turn that gear, and as you guys are going to expect, or indeed if I turn my shaft because it's all linked, it's all gonna move. Now as you can see, that's also given us a bit of movement in our secondary shaft there, which is ideal, because that is resultantly turning the pulley, if you notice, and at the end it's also moving the cam. So the pulley, as you can see, I've got two vertically aligned pulleys here, but they're not going to be complete without a belt, really, are they? So let's go in and insert our belt. So if you've already got a pre-made belt, you can just use where my mouse cursor is at the moment, the standard insert components dialog. Drop that down and choose to insert it, and you can mate it into place. But if, like me, you actually want to create the belt from scratch, that's pretty easy to do as well. Go to your assembly features, and in here you're going to find belt and chain. Now that's where we can create a belt, and believe it or not, a chain as well. If we click on belt, very simple selections again. Select the two or indeed more pulleys. You can have more than two pulleys, of course. Select them in there. SOLIDWORKS will automatically determine the size of your pulley, which it will insert there. You can choose to insert a belt location plane if you like. And this option here is actually quite nice, the driving option. Now what this does is if you look just under my mouse cursor, you'll see this belt is actually a size of 880.059. Now, I don't know about you, but sourcing an 880.059 belt, I would think would be quite difficult from any supplier. So what this option actually allows us to do is drive the size of our belt by allowing us to manually put a dimension in there. So we could just round that belt to 880 mil, which of course is going to be easier to find. Now it won't allow me to do it because I've got both of my pulleys fully fixed in space. You need to have at least 1 degree of freedom in there. So at the moment we'll just stick with the kind of awkward size belt. It's okay for the time being. This option at the bottom as well of create belt part, very useful to check. I'll show you why in just a moment. Because when I hit OK on this, what it allows me to do is specify a save location for my belt. That means I could use it in separate assemblies if I were to choose to. It also gives me, if I scroll right down to the bottom of my tree, a belt feature, which if I expand out, we actually have a belt part there, which is just a typical part. We can open that out, have a look at it. Now SOLIDWORKS by default will recognize a belt feature by just a single sketch line. Now to prove that to you guys, if I return to my assembly, what we'll find between the two pulleys, if I make my sketches shown, is just a sketch line. Now it will react as a belt, but it doesn't look very realistic, does it? So what we can do is go ahead and just choose to extrude that out. Let's say do it about the mid-plane to keep it centralized on the pulley. We'll make it 20 millimeters thick. And as for using the thin features to apply a wall thickness to it, or a belt thickness I guess that should be, let's just even make it 1 millimeter. World's thinnest belt, but again it doesn't really matter for the demonstration purposes here. Make it whatever you need it. If we then return back to that assembly, save it and return back, what we'll find is we now have a belt part between our two pulleys, which of course looks better than a sketch line. We can hide that sketch out now, just keep the belt part in place, and of course, moment of truth, if I turn my secondary shaft, you can see belt is turning, and that's also resultantly turning my second pulley. Now let's turn the view sketches back off just to clear up the display a little bit here. And we'll turn our attention to getting the cam following, the cam follower following the cam. So what I want to do here is have this cam follower follow the outer faces of my cam. And my thinking is, my logic here, is I'm going to have the cam follower bounce, and that's going to wave my flag around. So as you can probably guess, if we go into our mechanical mates, we do of course have a cam mechanical mate. Again, simple selections. Select the following faces of your cam, so the faces you want to be followed, outside faces usually. And for the cam follower, you want to select a sketch entity on there. Now what you'll see is I've actually got a sketch point on the end of my follower. And when I select that, the cam follower is just going to follow my chosen faces on the cam. So again, relatively straightforward, but does give a nice result. If I go ahead and turn that shaft now, as you would expect, cam turns, which resultantly makes the flag bounce. Excellent. Looking good. So that finishes off that little mechanism there. Let's continue on though, and we'll turn our attention to our universal joint. So I want these two yokes to turn in unison, and as we know, as you probably know I should say, if we were to physically create an assembly with a centralized spider, we can of course have that movement. But say you don't want to go to the efforts of creating all that with pins and a spider in the center and whatnot. Well, we can, under the mate dialog, choose under our mechanical mates to insert a universal joint mate. Now, not many people are aware of this one, but it's very handy to have, especially at the conceptual phase. What it allows us to do is just go ahead and select your two yokes, or whatever it is, whatever your geometry happens to be, and after that selection, they will turn in unison. So quite a handy one to have. Again, as I say, at the conceptual phase, very handy because it means you don't need to model up your centralized spider. You don't need to pin it together. You don't need to bother with all the mates. Very handy to know about. And to finish us up here, we want to secure that yoke in place with this bolt. Now, as we all know, we could just insert a coincident mate to get that into place, but that's no fun really, is it? And what if we want a more sort of realistic representation of that bolt being inserted? Well, this final mate of today of screw should come in very handy. The screw mate, again, quite a simple mate. Basically, it allows us to represent a screw or a bolt or whatever it happens to be being put into place. Again, very simple selections are required. Choose the thread face of the bolt or the screw and the receiving thread face. You can then stipulate if you want to control it by revolutions per millimeter or distance per revolution, and then go ahead and use a scale factor. We'll use a scale factor of 1 here, just to show you first of all. I tend to minimize it a little bit. I'll show you why in a moment. If I then add that in, go ahead and grab hold of my bolt and twist it, you'll see slowly, but it does start to taper into that hole there. As I say, it's a little bit slow, so if you go back in, make an edit to that screw mate, and I tend to minimize this, let's say make it 0.1, maybe a bit extreme, but it'll help emphasize what it does for you guys here. As you can see, just allows it to be put into place faster. Now that's particularly good, the screw mate I mean, if you are maybe creating an animation or any other purpose that you may have for wanting to realistically insert a screw or a bolt or whatever it happens to be. And there we go guys, got all our mechanical mates in place to match our assembly. And yeah, moment of truth. Let's turn it right back at the beginning and see if everything turns as we expect. And there we go. We literally have created the world's most elaborate flag waving machine. Don't say these webinars aren't informative and relevant. But yeah guys, I hope that's been very informative for you. Of course the model's a bit silly, but all those mates I can assure you are incredibly functional and indeed quite fun, as I found when you're creating a little mechanical machine like that. Very fun and can get quite addictive, do be warned. And that does bring us to the end of today's webinar. So give them a go for yourself guys, and thank you once again for tuning in. And of course, thank you for your continued support of our webinars. We do see we've got some frequent customers now, so thank you very much to you guys. We greatly appreciate it, we really do. Have a great weekend guys, and thanks again.